Solve the system of simultaneous linear differential equations given by dx by dt plus 5x minus 2y equals t, dy by dt plus 2x plus y equals 0. Given the condition x equals y equals 0 whenever t equals 0. In this set of linear differential equations, we have x and y are the dependent variable and the single independent variable is t. Such type of linear differential equations involving more than one dependent variable and a single independent variable will be called as simultaneous linear differential equations. We will have to find out solution corresponding to dependent variable x as well as dependent variable y. Let us introduce the differential operator capital D, which is derivative with respect to independent variable t, that is capital D equals d by dt. Using this differential operator, we have the first differential equation rewritten as d plus 5 acting on x minus 2y equals t, and the second differential equation can be rewritten as 2x plus d plus 1 acting on y equals 0. Now we will eliminate any one of the dependent variables. If we eliminate x, then we will have to multiply equation 1 using 2 on both LHS and RHS. Simultaneously, we will have to multiply equation 2 using the operator capital D plus 5. Once we eliminate x, we will obtain a differential equation involving y only, and we will solve the differential equation to find out the general solution y equals complementary function plus particular integral. When we perform 2 multiplied throughout equation 1 minus d plus 5 operated throughout equation 2, we will get this step. Here we have d plus 5 multiplied to 2x getting cancelled, and we are left out with 4 plus d plus 1 into d plus 5 into y with the negative sign taken common outside in the LHS equated to positive 2t. When the negative sign from the LHS is taken to RHS, we will obtain 4 plus d square plus 6d plus 9 acting on y equals negative 2t. Here d plus 1 into d plus 5 is equivalent to the operator d square plus 6d plus 9. By usual multiplication of linear factors, we can identify that these two operators are exactly the same. Now we will solve this differential equation to obtain the general solution corresponding to y. Here, when you replace capital D using m and equate the RHS to 0, we will obtain the auxiliary equation. Here we have auxiliary equation is obtained as m square plus 6m plus 9 equals 0, which has solution m equals minus 3, minus 3. Since we have repeated roots obtained for the auxiliary equation, the complementary function will be written as c1 plus c2 times t multiplied to e raised to negative 3t, where t is the independent variable. Now we will find out particular integral corresponding to this differential equation. We have pi equals 1 by f of d acting on minus 2t. We have f of d equals the operator capital D square plus 6d plus 9, which can also be written as d plus 3 the whole square. Therefore, pi equals 1 by d plus 3 the whole square acting on the RHS, which is minus 2t. When minus 2, which is a constant, is taken outside the operation of 1 by f of t, we have 1 by f of t acting on the input t. Since the input is of the form t raised to n, we will rewrite f of d as 1 plus phi of d and take it to the numerator as 1 plus phi of t the whole inverse and use the binomial expansion. Here when you take the constant 3 square outside this operator, it becomes d plus 3 the whole square equals 3 square multiplied to d by 3 plus 1 the whole square. Minus 2, which is already taken outside the operation of 1 by f of t, along with 3 square which appears in the denominator becomes negative 2 by 9, and we have d by 3 plus 1 the whole square when taken to the numerator becomes 1 plus d by 3 the whole raised to minus 2, which acts on the input t. We will expand 1 plus d by 3 the whole raised to minus 2 using binomial expansion, and we obtain 1 minus 2d by 3 plus etc. Here we have considered till the term d raised to 1 because the input has the power equal to 1. All other powers of differential operator will give us 0 as the answer when operated on t. Therefore, required pi will be minus 2 by 9 multiplied to t plus 2 by 9 multiplied to 2 by 3 multiplied to derivative of t, which is 1. We get pi equals negative 2t by 9 plus 4 by 27. Therefore, general solution will be y equals c1 plus c2t multiplied to e raised to negative 3t minus 2t by 9 plus 4 by 27. Now we will have to find out general solution corresponding to x. For that, we will substitute the value of y in equation 2. Recall that equation 2 was 2x plus d plus 1 acting on y equals 0. From this equation, we will obtain x equals minus 1 by 2 times dy plus y, where dy indicates derivative of y. From this expression of y, we can find out derivative of y. In the RHS, we will carry out differentiation with respect to independent variable t. For the first term, we will have to make use of product rule. And for the term minus 2t by 9, the derivative will be minus 2 by 9. This term being constant will give us derivative equals 0. Hence, we have dy equals c1 plus c2t multiplied to negative 3 times e raised to negative 3t plus c2 multiplied to e raised to negative 3t minus 2 by 9. Now, in this equation for x, we will give the expression for dy as well as y. Dy is found here and y is already given by the general solution. On simplification, we obtain x equals t by 9 plus 1 by 27 plus e raised to negative 3 multiplied to c1 plus c2t plus negative c2 by 2, which is the required general solution corresponding to x. Having obtained the desired solutions corresponding to x and y, now we will make use of the condition given in the question in order to find out the particular values of constants. In our question, we have been given with the condition that both the dependent variables x and y assumes the value 0 whenever the independent variable t equals 0. In our equation 3, which corresponds to general solution of y, we will give the condition y equals 0 and t equals 0, from which we obtain c1 equals negative 4 by 27. Similarly, in this equation, we will give x equals 0 and t equals 0, which will give us the value of constant c2. We get c2 equals negative 2 by 9. Now we will revisit the equation 3, which is the general solution corresponding to y, and we will give values of c1 and c2. Similarly, values of c1 and c2 will be given in equation 5, which corresponds to general solution corresponding to the dependent variable x. Giving the particular values for constants, we obtain x equals minus 1 by 27 multiplied to 1 plus 6t plus 1 by 27 times 1 plus 3t. Similarly, on simplification, giving the values of c1 and c2, we obtain y equals minus 2 by 27 times 2 plus 3t multiplied to e raised to negative 3t plus 2 by 27 times 2 minus 3t. And these expressions of x and y are the required solutions.